Hello guys, so in this video we'll cover the electron arrangement as well as electromagnetic spectrum and other chemistry related things. So first of all we need to describe the electromagnetic spectrum, and students should be able to identify the ultraviolet, infrared and visible regions and to describe the variation in wavelength, frequency and energy across the spectrum.
Okay. Electromagnetic spectrum is a continuous spectrum of all the frequencies of electromagnetic radiation. As we shift from radio waves to ultraviolet waves, we can see that the frequency increases. Frequency is the number of waves per time. Ultraviolet waves also have a shorter wavelength than infrared waves. A wavelength is the distance between one trough, which is the bottom of the wave, to the other trough. Or from one crest, which is at the top of the wave, to another crest. In addition, infrared waves have a lesser amount of energy than ultraviolet waves.
So we're now going to talk about some equations. The first equation we're going to talk about deals with frequency and wavelength. In this equation, the speed of light, represented by c, equals lambda nu. Now here, lambda represents the wavelength and nu represents the frequency. Thus, you can see that wavelength and frequency are inversely related. The next equation we're going to talk about deals with energy. In this equation, energy equals Planck's constant, which is provided to you, times the frequency of the wavelength. This will then give you the energy of the photon emitted. Okay, so now we're going to talk about the different series of light. We have the Balmer series, the Lyman series, and the Paschen series. The Balmer series represents the spectrum of visible light, in which the electrons fall to the n equals 2 energy level. The Paschen series represents the infrared light and a fall to the energy level n equals 3. The Lyman series represents the ultraviolet light and a fall to the energy level n equals 1. The Lyman series thus has the most energy, the Paschen series has the least, and the Balmer is in between.
When an electron becomes excited, it jumps from its ground state. When an electron becomes excited, it leaves its ground state and jumps up to another energy level with the provided energy. As it falls back down to the ground state, that energy is released in a form of a photon. A photon is a particle representing a quantum of light or other electromagnetic radiation.
Students must also distinguish between an emission spectrum and a line spectrum.
So each element then also has an emission spectrum and an absorption spectrum. The lines of the emission spectrum represent the frequencies of light emitted as an electron jumps from a higher to a lower energy level. An absorption spectrum depicts the frequencies of energy absorbed, with its missing lines corresponding to that sample's emission spectrum. Thus here we have the hydrogen emission spectrum. As you can see, the frequencies converge at a higher frequency, and the absorption spectrum of hydrogen would be similar to this in that it's a full continuous spectrum, but it's not, because the missing lines would be those depicted here in the emission spectrum.
You must be able to explain how the lines of in the emission spectrum of hydrogen are related to electron energy levels. Students should be able to draw energy level diagrams, show transitions between different energy levels, and recognize that the lines in the line spectrum are directly related to these differences. An understanding of convergence is expected. Series should be considered in the ultraviolet, visible, and infrared regions, but calculations, knowledge of quantum numbers, and historical references will not be assessed in IB.
The emission spectrum is a line spectrum in that it shows specific values of frequencies. In this example of the hydrogen emission spectrum, you can see that the lines converge at higher frequencies. The entire electromagnetic radiation spectrum is a continuous spectrum. The electron arrangement for atoms, as described by the IV, is represented as the number of valence electrons an atom has. Take neon, for example. It is a noble gas, and its electron arrangement is 2-8, because it has 2 electrons in its first orbital and a full octet in its second orbital. However, take aluminium, which is not a noble gas. Its electron arrangement is 2-8-3, because it only has 3 electrons in its third orbital. The IV states that you only need to go up to the atomic number 20, which is calcium, because after that you have to learn d orbitals, which is too complicated for you to know.
So how does all this relate to the flame test colors? When samples of different elements are placed in a flame, energy is being supplied to its atoms. As a result, the electrons of the atoms move to a higher energy state. As they fall back down to their ground state, they emit a photon of light with a specific frequency to the element. Each element then emits a different frequency of light due to their unique electron arrangements and orbitals. The different colors produced by the flame test can then be used to identify the element being burned. For instance, lithium burns a deep crimson red. Sodium creates a yellow flame. Potassium creates a purple color. Calcium burns an orange-red color. Strontium produces a bright red flame. Barium produces a bright Voldemort green flame. And lastly, copper results in a blue-green color.